So today we're starting to talk about the definite integral. We talked about the indefinite integral earlier in the chapter. Yesterday, in the last section, we discovered how to find the exact area under a curve using this limit. Limit as n approaches infinity of the sum, k equals 1 to n, of base times height of all those rectangles that we would use. So as the number of rectangles increased, and we took the limit as that number of rectangles approached infinity, we found the exact area under the graph from A to B. And like I said earlier, we talked about the indefinite integral, and these are actually kind of connected because the definite integral is like the indefinite integral, only it has an a and a b that are attached to that integral sign, and that a and b are these two letters right here, the beginning and end of that area, because the definite integral from a to b of f of x dx actually equals the exact area under the curve f of x from x equals a to x equals b. So basically this big, nasty, ugly limit that we worked through by hand yesterday is equivalent to the definite integral from a to b of f of x dx. Alright, that integral, remember how it looks like an S? Well, this is a sum, right? So there's a little bit of connection there. I don't know if that was on purpose or not, but this is actually like the limit of the sum of all those areas of the rectangles. We'll talk a little bit more down the road about how to evaluate definite integrals, but right now we're just talking about the connection that those definite integrals represent the area under the curve. And when I say area under the curve, that means the area between the curve and the x-axis. The area between the graph or the curve and the x-axis. We did a little bit of this the other day. If we look at our first example down here, it asks us to find the definite integral from 0 to 6 of f of x dx. That just means find the area under this graph from 0 to 6. So from 0 to 6, under this line, we just end up with a big rectangle. Alright, so right now we're starting off with basic ones that we can find geometrically. Like I said, later we'll learn how to do it without area formula. But here we've got a base of 6, height of 4, so our area comes out to be 24. Then our second one, definite integral from 0 to 8, under this line, we end up with a trapezoid. And we have one base that's 3, one that is 7, and then a height of 8. So 1/2 times 3 plus 7 times 8, we get an area of 40 for this one. And then our last one is the area under the curve from 0 to 5. This time, part of the graph is below the x-axis, but we're still finding the area between the graph and the x-axis. So we're finding this triangle, and then we're finding this triangle over here as well. Now, when the graph is under the x-axis, we're going to have a negative area. If the graph is below the x-axis, means we're going to have a negative area. And the reason is that one of the dimensions is going to be negative. So for example, this triangle, this height is -2. The base would be +2. So our area would be 1/2 times -2 times 2. So we get an area of -2 for this triangle. And then this one, we get 1/2 1/2 times 1/2 times 3 times 3. We get 9/2 or 4.5. So we have to combine these two. To get the definite angle from 0 to 5, we're going to have